Okay, in this segment, what we're going to use is basically this idea of geometric series to give us our first power series representation of a specific function, that function being the function f of x of 1 over 1 minus x. So let's review a couple ideas from geometric series first. So if we remember our geometric series, for example, we could write this as a series from n equals 1 to infinity of, say, something like 1/2 to the n minus 1. And in this case, we notice that, well, the absolute value of r is equal to 1/2, which is less than 1, so this converges. And the second thing we notice about geometric series is when it converges, we know what it converges to. So if you remember, our formula for geometric series to converge was equal to a over 1 minus r. And for this particular problem, our a is just 1, and our r is 1/2. Okay, let's generalize this just a little bit. And the first thing we're going to do to generalize is start the series at n equals 0. So if we start the series at n equals 0, we need to make sure we capture the same amount of terms for our geometric series. So again, from this series up top, when n equaled 0, when n equaled 1, we got just 1. When n equaled 2, we got plus 1/2. When n equaled 3, we got plus 1 over 2 squared. When n equaled 4, we got plus 1 over 2 cubed. And in this case, we can see, well, the power that we need upstairs here is to give us the same terms that the original series gave from up here. And well, basically, if we just start our series at n equals 0 instead of n equals 1, that shifts our power from n minus 1 to n. So that's the first thing. If you don't fully understand that index shifting, I'm not going to focus on that too much in this particular course. The second thing we can notice is, well, this converged because r was less than 1 in absolute value. Let's broaden this just a little bit. So for a general r, again, not saying that r is a specific number now. We have this geometric series looking like the series from n equals 0 to infinity of now r raised to the power of n. Okay, and again, our a here is equal to 1. Our r, well, as silly as it sounds, that's equal to r. And we know if this converges, what it converges to. It converges to a, which is 1, over 1 minus r, which in this case is r. So at this point, we're dancing around a lot of ideas. Okay, we're saying, hey, if I just write a general geometric series from n equals 0 to infinity of r to the n, my a is 1. This converges if r is less than 1 in absolute values, and hey, I know what it converges to. So the next thing, let r equal x. And let's call this a function now. Say I have a function of x. And again, I'm just taking our geometric series that we just analyzed from n equals 0 to infinity, and I'm just replacing those r's with x's. And this is looking more along the lines of a power series. And well, we said, you know what? If this power series converges, basically based on the analysis we did in this general case for r, in this case, it would mean x has to be less than 1 in absolute values for it to converge. And you know what? If x is less than 1 in absolute values, based on the geometric series ideas we used up top, we know it converges to 1 over 1 minus x. So why is this important? If we look at it the opposite way, we have that 1 over 1 minus x is equal to that power series when n equals 0 to infinity of x to the n when x is less than 1 in absolute values. And this, friends, is our first power series representation of a function. We have the function 1 over 1 minus x is equal to the power series from n equals 0 to infinity of just x to the n when x in absolute value is less than 1. So this is the first power series for us to commit to memory. And also, just so this is clear, we're basically saying, you know what? This function f of x, that's 1 over 1 minus x, I can represent it as an infinite power series or an infinite sum of x to the n as long as x in absolute value is less than 1. So we have now a new equivalence. This function we may have seen before in our mathematical endeavors is actually equal to this power series as long as x in absolute values is less than 1. And if we're just handed this power series, we could see why x has to be less than or equal to 1. If we just hit it with ratio tests like we did in the previous video. So let's do that very quickly. If we hit this with ratio test, well, the limit as n goes to infinity of the next term in the series, which is just x to the n plus 1, all over x to the n. Well, this is equal to the limit as n goes to infinity of just the absolute value of x after we cancel out factors of x to the n in both the numerator and denominator. And well, what we need this limit to equal or be less than is less than 1. But this limit, since it doesn't depend on any n's anywhere, this is just equal to the absolute value of x that we need to be less than 1 in order to converge. And well, if we test the endpoints, being the endpoints of x equals minus 1 or x equals 1, these will result in divergence. They're not going to satisfy the test for divergence. So this is why we can come full circle now. This function that we have up top, f of x, if we just look at this, well, if we are trying to put values of x into this function to get meaningful things back, if x equals 1, we're in trouble. Because we get a divide by 0 looking thing. So this also suggests that the furthest we could reach our hands out if we're centered at 0 in our power series is an arm's length of 1. So when we write this equal to that power series, through the power series analysis, not the absolute value of x. But through the power series analysis, we're popping out that, hey, you know what? At x equals 1, something bad happens, which we can also see from the way the function's written itself. So this is the first power series that we need to commit to memory. And what we're going to do next is basically use this power series to tell us other power series of similar looking functions. Check out those videos.